Hello and welcome to problem solving session of total internal reflection and critical angle. We discussed this in our last video, and if you haven't watched that, please watch that first before we proceed with the problem. So today we are going to solve few problems about total internal reflection and critical angle at which it happens. So these are very important concepts, and usually you get a question in the exam which will check for this. So please pay attention and enjoy. So here we have a question from IIT JEE 2003. A ray of light is incident at a glass water interface at an angle I. So here is our glass, here is our water, and the ray of light is getting interfaced at an angle I. It emerges finally parallel to the surface of water. So parallel to the surface of water, so it is going like this and sort of emerging from there. So this is what it is happening. The ray of light is coming like this and sort of finally coming out like this, which means there is a total internal reflection happening over here. So we need to find the value of refractive index of the glass, which is here, and we have options. So to tackle this, first we have to understand that the total internal reflection is happening here. Hence we need to somehow write condition for total internal reflection here, and then the ray is passing through water and ray is incident here. Now as we discussed in the Snell's law, it has two parts, and we can write one part from here and another part from here, and we can ignore the in between, still the law will be valid, right? So let's try and write the Snell's law here and here and see what we have, right? So at A, Snell's law, for the left hand side only we'll write, so this is sine 90 into refractive index of air is 1, and for the second part we'll write the Snell's law here, right? So we'll say sine of I into the refractive index of the glass, right? Now we have to find refractive index of glass, so this is unknown, so we will rewrite the equation. Sine 91 divided by sine I, okay, and 1 divided by sine I, and we can find it here. So this is our answer, okay. So the important point is that you do not need to write a lot of Snell's law here, here, here. You can simply write one part from this at the end and another part from this side, and you can always equate that in one simple equation. You will be able to solve the problem. So let's move to the next one. Now a light beam is traveling from region 1 to 4, okay. The refractive index of regions are given and not etc. The angle of incidence theta for which the beam just misses entering the region 4. This is what we should be looking for. So the ray of light will come here, the reflection will happen, and finally it will not be able to enter the region 4, right? Which means the total internal reflection will happen over here, right, for a particular angle. So you can write one part of Snell's law here, and we need to find the theta. So if we can write another part of Snell's law here, with this equation we should be able to solve the problem, right? So at point A, we'll write and naught by 8 into sine 90s, and we'll write another part over here. Simply put, sine theta into and naught, okay. And we need to find sine theta. Sine theta will be, and naught will cancel, simply sine 90 by 8, that's going to be 1 by 8. So theta will be sine inverse 1 by 8, and that should be our answer here again, P, okay. So without worrying about what happened in between, we can simply write the Snell's law at 2 point any 2 points and actually equate them depending upon what is unknown and what we need to find out. So next question, a parallel beam of light is incident from air to an angle alpha on the side PQ of a right angled triangular prism of refractive index n. Okay, so we have this right angle prism, so we know that this is 90 degree and ray of light is coming like this, so parallel sort of like that, and it's coming at an angle of incidence alpha. So this is our normal. Okay, so let's try and redraw this so that we can do the thing. So this is our prism, and what we know sort of, this is 90, this is theta, this must be 90 minus theta, that we know, and we also know the ray of light is getting incident at angle alpha. So first we need to draw our normal. To this normal, let me choose another color. So the ray of light is going to come from here, yeah, at a particular angle alpha. This is going to be alpha. Remember, from the normal we write, and alpha has a minimum value of, so light undergoes total internal reflection in the prism at phase PR, right? So this is PQR, right? So in somewhere here it will get totally internally reflected, and then we just have to find theta. Okay, so we need to find a relationship using Snell's law between the unknown, which is this one, and this is known, and then the refractive index is also given, which is, sorry, n is equal to root. Okay, now this photo seems pretty confusing because the ray of light seems to be passing parallel to the base, but it is not getting totally internally reflected because this angle is not 90 degree, right? So possibly it is slightly bigger angle, so ray of light is coming at a slightly bigger angle, and then it is going to get refracted here first. So let's draw a diagram. So because it is a denser medium, it will get towards the base, then we're going to come here and hit, and then we will need our normal over here. Okay, and now it will get totally internally reflected, which means pass like this. So this angle is going to be 90 degrees. Right. So we definitely will need to write a Snell's law here, and we need to possibly find this angle, which is unknown, to sort of find relationship between them, right? So this is how we'll proceed and think about the problem. And let's write some equation to see where we can go from the whatever information is available, right? So first, let's apply this Snell's law at this point. Okay, let's call it A, and we can write alpha is given at 45. Okay, so in the air, 1 into sine of alpha, which is 45, and this one, this angle is unknown, which is angle of refraction R. Okay, so we can write prism root 2 into sine R1, sorry, R, right? Sine of R is going to be sine 45 by root 2, and R will come out to be 30 degrees. Okay, so you can do this simple over there. Now we know this, right? So let's law the Snell's law here, B. So at B, we are going to be writing root 2 sine C will be equal to 1 into sine 90. Okay, this is going to be equal to 1. And now we need to somehow find a relationship between C and theta. So first let's find out C, because we can get that here easily. First, C, so sine C is 1 by root 2, hence C is going to be 45 degrees, right? Now with the C known, using simple geometry, probably we'll be able to figure out theta. So let's look at this triangle which is forming here to start our guesses. Yeah. So if this is 90, this one is going to be 90 minus theta. Okay, and this one, let's call it angle unknown, say beta. Okay, so beta is going to be equal to, because it's a straight line, so 180 minus 90 minus theta, so minus, so it's going to be 90 plus theta. Okay, now we have again this triangle here, so r is known, right? So we can write for this triangle, yeah, for this triangle, right? For this triangle we write, so r is 45, okay, sorry, 30. So r is, so r is found out, r is 30, so r plus beta, right, plus 90 minus c, right? So this angle is 90 minus c plus 90 minus c, because this is perpendicular, right, is going to be equal to 180. We simply plug in r is equal to 30, beta is here 90 plus theta plus 90 minus c is going to be equal to 100. Okay, now we have to just find our theta. And theta will come out to be 15 degrees. Make simple arithmetic, and now we can pick up our option. Yeah, so which is here, option number A. So see, geometrical optics problem has two parts. As I said, there's a physics, right, plus also geometry. A lot of things you have to mix them and basically find out your answer. So we did the physics, we wrote Snell's law here and here, we got some equations, and we used geometry to solve the problem, right, to arrive at the answer. So let's move on to the next one. So the beam of light consisting of red, green, blue colors, right? So we have three wavelengths basically here. We have red, dark green, and blue. Okay. So these three wavelengths are coming from this side. The refractive index of material of the prism. So as we know, for different wavelengths we have different refractive index, right? So for the red one is 1.39. For the green one it's 1.44. And for the blue one it is 1.47. Now what the prism will do, right? So what will happen, so it says, gives us hint, separate part of red color from the green, etc., separate part of blue color from red and green colors, right? The prism will do like that. So I think when you look at this problem, you want to sort of why it will happen, right? So maybe the total internal reflection is happening and not all the light waves are sort of getting from here, right, and for sort of getting reflected, right? Maybe some of it is coming inside. So let's find out that condition of the total internal reflection, and then probably will help us find out the solution to the problem, right? So let's write our equations. First thing first, we will need our normal. Okay, now a straight light is going to come like this, different color. So here is our ray of light which is going to come like this. So there is going to be no refraction here because it's coming straight at 90. Okay, now this is our angle of incidence. We do not know it right now, and it will go like this. Okay, so this is going to be 90. So let's write the Snell's law. From this side, sine 90 into 1 is the refractive index of the air, and this side is a critical angle, right? So I sine I critical into the refractive index of the prism, which is unknown, right? So we write NP, which is unknown. So let's find out NP, and NP will turn out to be 1 by sine I. Okay, now do we know sine I? Yes, using geometry we can. So this is 90 and this is 45. So this one is also going to be 45. Hence, this one is going to be 45 and this I is also going to be 45. So 1 by sine 45. Hence, NP is 1.414, right? So this is a critical angle, right? So if the refractive index is more than this, basically the light will get totally internally reflected. If it is less than that, right, it will pass through, which means that the red light, right, so the red one will pass through and it will also get reflected here like this, right? But the blue and green one will totally internally reflected. Hence, it is separating the separate part of red color from green and blue, right? Because red color is getting reflected and sort of rest all is getting reflected back, right? So total India. So let's check the answers, other options. So the correct answer here is A. Okay. Correct option here is A. Now let's move to the next problem. Now, if you remember, I told you that we can always build light up pipes, right? Where we can send and transmit light from one point to another if the light is getting totally reflected inside the pipe, right? Now, this problem is something like that, right? So let's look at it. So a glass rod of rectangular cross section, right? So one information is that it has a rectangular configuration and a parallel beam of light falls perpendicularly to the flat surface A. So this is surface A. Now light is going to fall parallelly here. Okay. Determine the minimum value of ratio R. So R is okay the radius of this curvature and D is the width, for which all light entering the glass through the surface A, right, will come out here surface B. So no light will pass from this side, right? How is this possible? Only when a light ray coming here like this is getting totally internally reflected here, right? Then again reflection, again reflection, again reflection, and something like that, right? So it will do only when there's a total internal reflection happening and no more information is provided. So we'll have to sort of think that how we are going to tackle the problem, right? So one of the attempts I always do in problem solving is to help you think that how you can solve the problem, right? Now here it's quite a general case, right? So how we are going to approach it is basically there is very few things which are known, right? So I'll first like to write the knowns, which is have a refractive index of glass, okay, which is 1.5 mu g or ng, whatever you want to call it. Now we know that light of ray is coming like this, right? So let's look at a couple of options here. What is happening, right? So maybe by doing that, we'll be able to figure out a way, right? So let's say the light is coming. Light is coming like this. So of course it will not get, nothing will happen here, right? At this point, will pass through. Then we expect a total internal reflection to happen at this point. So let's draw the perpendicular and we know that it will cut at the center, right? So that's why the circular path is given, right? So now let this angle here, so it will deviate at this angle only, right? Slightly bigger. Then we will have again perpendicular, then on the same angle and so on and so forth, right? Now if we put the light ray over here, let's see what happens, right? So we are looking at the extremes to understand what's happening in between, and that's what you should always try, right? So now let's send the light beam from this side. We know it is going to be parallel from this side towards the edge. It goes right. So now we'll need our normal, and the normal is going to be touching the center, that we know. And now this is our angle of incidence. We get somewhere, right? Now you will observe that this angle is smaller than this one, right? We know that there is a critical angle is, we need the minimum value of that angle, right? So if we can prove that the light ray is actually getting reflected, totally reflected over here, right? Over here, then by default for all other rays which are on this side, left side, is actually inserting on a higher angle, right? So this is our critical angle, right? So if we can prove that the ray which is just touching the the glass on this side is also getting totally reflected, basically all the light rays in the pipe will get totally reflected and hence will come out on the B side, right? So this is our point where we want to write Snell's law. Okay, and so this is our normal. So this is 90 and this is our critical angle. Okay, so we know the refractive index of the prism, so 1.5 to sine I critical is going to be equal to, very easy, 90 will be equal to 1. Hence sine I critical divided by 1.5, right? We have it here. So let's put it in the variable form only. So 1 by, let's say, the refractive index n, right, for now. So this is the right way of writing the critical angle equation, because this is the minimum angle we want to find out, and we already said that all other angle at which the light is going to come is going to be greater than that. So now I think the physics part is over. So now we could really think about the geometry to find the relationship between D, which is given R, and this N, right? And once we are able to do that, we'll be able to arrive at the answer. So now notice here that this ray of light is coming like that, which is just touching the circle, right? And then again it is getting reflected at the same angle, right? Which means this one will also touch the circle, right? So it's time to probably redraw our picture correctly so that we're able to figure that out. Okay, so we are going to redraw our ray. So this is also going to be touching here, right? So that this angle and this angle is okay and similar. So now probably we'll be able to write some equation here. So this is perpendicular, so this is going to be 90. Okay, there's no doubt about that. So this angle is 90. So let's draw our triangle here. So this is our triangle, and this angle is 90. This angle is I, right? So this one is going to be like 90 minus I. Okay, and this one we know, right? This is this one. This one is R, and this distance from here to here, right, is our R plus T. Okay, so in this triangle, right angle triangle, what is going to be? Sine I, right? Sine I is going to be equal to, sine I is going to be equal to R divided by R plus T. This is the critical angle here, right? So now we can equate that. So what we're trying to say is that if R by R plus T is going to be greater than 1 by N, basically we'll have critical internal reflection here, and the ray of light, any of them from the left hand side, will come through surface A and will emerge from surface B. So this is our condition, right? So this has to be greater than equal to, so let's correct that. Okay, so now we know all of them, so we need to determine the minimum value of ratio R by D. Okay, so that is going to be equal to, this equation is going to be equal to R by D has to be greater than equal to 1 divided by N minus 1. Okay, we'll do the maths. It's very simple. It means that it's going to be 1 divided by N, we know already, right? It's 1.5, 5 minus 1, and this is equal to 2. So whenever we'll have this ratio R by D greater than equal to 2, so whenever we have this R by D greater than equal to 2, basically we'll have the total inner reflection, and basically our light will come from here and go from here, and that's what the problem is asking. So as you noticed, again, basically it has two parts. Part is physics, and then the second part is basically geometry. And by using these two things, we can solve the problem. So moving on to our next problem, says there's a small coin lies at the bottom of a tank of water at depth D. Okay. Determine the size of a piece of a cardboard cover when floating on the surface of the water directly above the coin. A coin cannot be viewed from the air. So that coin cannot be viewed from the air, right? So which means that So let's try and draw it first. So we have tank probably like this. Okay, tank of water, and we have water up to here. Okay, the coin is lying over here. Sometimes you won't get a diagram, so you need to draw that. So here is our coin lying, depth given D. We know that D. This is water. We know the refractive index roughly 1.5. So N of water, yeah, is known. Now, in order to view the coin from the top, a ray of light has to travel from here to here, get refracted, and then you will be able to view the coin. Now, there are two ways we can stop that from happening. Okay, so we can put cardboard all the way like this, right? Then nobody will be able to view the coin from the air, right? But if we just have to see like what is the minimum cover, right? So we know that at certain angle this, right? There is going to be total internal reflection, and hence we need to have a smaller cardboard, yeah, something like that. With that, when the total internal reflection will happen, all the ray of light after this angle I will get internally reflected on both the sides, okay, and then nobody can view the coin from the top, okay. So that's the condition we are looking for. So let's try and draw the diagram clean and basically see that we can solve the problem. Okay, so this is our surface. Let's draw the cardboard. Let's say it's something like this, and it has to be circular, right? So that we cannot view the coin from any of the sides. And let's say here is our coin. So this will be the center of the cardboard as well. Let's say that. Now let's draw a normal, and this is going to be I critical. At this point, the total internal reflection will happen on all the sides of the cardboard, and then no ray of light in the visible range is going to pass, and nobody will be able to see the coin, right? Now given is basically your refractive index of water, and water, and we know the depth. Probably we are going to use that in the geometry, but very easily, first thing first, we need to write the Snell's law here, the critical angle in mind. We are going to say N of water into sine IC has to be greater than equal to, it's all air, so 1 into sine 90 has to be greater than or equal to 1. So sine IC is a known and W is known. So now our condition for sine IC, probably we need to use some geometry. Let's do that. This is IC, and this is going to be 90. Now this is circular, so let's R be the radius of the cardboard, right? So R should be also known. So somehow we need to write the sine IC in terms of R and D. I think we can simply do that. So this is D, this is R. So this is going to be R square plus D square and the root, and sine IC and W to sine IC is going to be R divided by R square plus D square greater than equal to 1. We need to find that R we know, and W and D. Putting it simply there, we can say that by solving this equation, R is going to be equal to D by NW square minus 1 under root. Don't know how it happened, just square it up. Right. Take it off this side, and then we'll arrive at this, right? So this is the answer. So this should be the radius of the cardboard. It has to be circular, matching at the center, so the coin has to lie right at the center of that cardboard. And then if you have that basically of this dimension, nobody will be able to see the coin at the bottom. So this kind of problems always comes, so please keep in mind. And let's go to our next problem. It says that a glass prism is lowered into water, Okay, this is a prism which is lowered into the water. The refractive index of the glass is given 1.5. At what angle alpha? This alpha. Okay, will be the beam of light incident normally to the AB. So the ray of light is coming like this. Will reach AC entirely. Okay. Now it's coming from here, right? So nothing will happen here, but in here there is a chance of total internal reflection, right? So there has to be a critical angle here. If it get reflected from here, okay, it will pass this. A reflection will happen. You will be able to see the ray of light on this side, right? Now, if that angle is more than that, this critical angle, right, we will not be able to sort of see the ray of light. So this is our critical angle, okay? So now let's try and write that equation again. Simply put, whatever information we have, so this is 90, this is 90, this is alpha, this is 90 minus alpha, hence our angle of incidence here, right, the critical angle is also equal to alpha. Okay, so I is also equal to alpha. So if we can find I, we'll be able to find alpha, and that's what we want to find out. We know the refractive index here, so we'll write n sine I, and it's going to be here. This is 90, this side is water, so water, let's say NW, and water into sine 90. Okay, so this is 1. Sine I has to be greater than equal to, right, NW divided by N. So we know this ratio, we can find I, and I is equal to greater than equal to sine inverse of NW by N. And if we know this NW and N alpha, basically we can find that I is somewhere around 60 degrees. Okay, so it's all the matter of just understanding that from where the ray of light is coming, how it is interacting with the medium, where the interface is, and what will happen, what will not happen, and if there is a critical angle because of which the total internal reflection is happening. We just find that out, and basically by writing a simple equation, we can solve the problem.